Oh, hey, I didn't see you there. Welcome to Freak Laboratories. If you follow me, I have a special project to show you that we've been working on in the garage. Oh, hey, Caleb. I didn't see you there. Hey, why don't we explain what the heck is going on? Okay. Welcome. This is our Ballista, named Rachel. As you can see, it's a superstar. Really, all we have here is just a couple 2x10s, a couple 2x4s on the outside. It's just 2-inch stock, 5.5 actual dimension by 1.5 inches. We got some spacers in the middle so that we can have a channel all the way for our bolt to run down without actually having to cut one in. We got these arms put out at 45 degrees, 45 inches long, coming out of the base. That means the total width of this thing is about, I don't know, just under 60 inches across. Then we got eye bolts hooking our band, as you can see, across. And then this puppy, as you can see, there's a hole right here and another hole right here. So we have a pin. We take that out. We take this pin out and drop the angle or raise the angle up to 45 degrees right here. And then lock it back in place. And you can shoot 30 and under and 45 degrees to get maximum altitude. Down here, as you can see, we've got a handle so that we can actually lift the thing up. Around. We got a sight right here that only works if you tilt it up. It's not really that practical, just for cool points. And then we got a trigger right here. The trigger mechanism is styled after a medieval crossbow trigger, a wheel trigger, and made out of 3/16 inch flat bore. We've got some bronze washers in there and a trigger box that's actually in there, sandwiched in. And we got the trigger itself down here. Basically, the trigger has a flat piece of metal going like that, then engages on a cutout on this wheel right here, and engages on that flat part. So any force this way is transmitted right into the pin that pivots this trigger and that one down there, so it can't actually go forward. We have a door hinge down here so that we can take the pin out on the other side
and raise it.
Yeah, and we can also just hinge it for that adjustable angle system. Here's our bands, exercise bands, a lot of them, and wound up really tightly. And then we've got some cable here on top of reinforcements and zip ties. So this actually interfaces with the trigger, hooks on right there. We'll go ahead and give you a demonstration. Okay, so that's it cocked. Anyway, so yeah, like I was saying earlier, you got a sight here in case you want to, peel your eyes. But anyway, those are the basics of it. We've got some wheels in the front on a central axle that helps us move it, so that you can do this. But we can't actually get it out of the garage to show you it shoot at this angle because it's too tall. It's about 8 feet tall at this point.
So who wants to go shoot this thing?
Let's all go to the lobby.
Yeah, let's go shoot it. Yeah.
All right, so
fire.
We said we had a sight earlier, so we can roll this boy if we want it under 30 degrees. We got a sight here, aiming for the pine tree. Knocked him. Wow.
That would have probably really hurt somebody if we hit them.
Yeah. All right. Hey, Steven.
Hey, man, what's up?
Wow. So here we've got a Brian technical specs lacrosse ball.
Yeah.
Pole in it, just a broom handle. Anyway.
So let's launch this stuff.
Yeah, we want to reduce friction, so we put a little paper towel in the
Otherwise, the ball. Key tips, guys. You can never forget your safety goggles. You might die otherwise.
Don't call me a safety Sally again, Steven.
All right, that's not his name.
All right. Got it set in the groove.
Is everyone ready for this?
Count down.
Let's watch this.
All right, 3, 2, count down.
3, 2, 1.
Whoa.
We did it. All right.
Sick.
Are you ready for this?
Yeah.
Get back, stay back.
Got all sorts of projectiles. Here's
It has a kick.
the golf ball on a longer pole for experimentation.
Watch
No.
your faces.
Safety squints on.
Safety second.
All right, shall we
See?
get a countdown?
Safety squints on.
Countdown.
6,
3,
5, 4.
3.
Oh.
Oh my gosh.
Whoa.
Did you guys see that?
Becky.
Wow. Wow, that really did shoot far.
Yes, it did. But just how far is the question?
Let me check. I can't. I don't know. Let's find out.
Let's do the math.
Whoa, let's do the math.
Cool story. So we got the K value, right? That was found, but we took a weight like this, like a scale, and we take a weight on top of it, right? And we take our band, hook our band on it, and pull up from the ground. We have a given point, and so that's say our rest. We pull up a little bit more, and that's going to be delta x is our displacement, which is the difference between these two, right? That's delta x, measured from the ground as well. Then we check down on the scale, and we see how much the weight has changed, and that's the force. Convert that to newtons, and you can get your newtons per meter measured on your delta x. Take the average of a couple points. We got 457 newtons per meter on our bands. So anyway, cool story. So here's our ballista, just a quick model. We got 45 degrees here. Anyway, whatever. This is our distance here. That's our total distance from what would be rest of the bands to the lock on the trigger back here. That's 1.6 meters. But the way that our ballista is built, we have a piece that interjects here that arrests some of the elastic energy. So we actually lose 0.2286 meters of displacement on the bands for our delta x. So anyway, what we do here to find our elastic potential energy in total, we only want the elastic potential energy in that direction because that's the only one that's going to be propelling the ball forward, because it's on the actual axis. Because you have vectors here, you've got elastic energy in that way and in that way, and you add them together, and we only want this one. It's in the direction. So we do our total elastic potential energy. So we do 1/2 kxt squared minus 1/2 kxl squared, lost total. And then we get 584 joules here, which is just 457 times 1.6, blah, 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 blah. And we subtract 11.94 joules, and we get 573.02 joules as our elastic potential energy. All right, cool story. Bob's your uncle. You got, so the kinetic energy from the last one, you got one band, like that. We said that was kinetic energy there, but we got two of them, so we multiply 573.02 by 2. Anyway, cool. And we say that's our elastic potential energy in total, and that's going to equal kinetic energy because energy is conserved. So 2 times 573.02 equals the formula for kinetic energy. Solve for VI. We know the mass of our shot, which is the ball on the end of a broom handle. That's 0.8 kilograms, so solve that. For VI with 0.8 kilograms, you get 53.53 meters a second. Is our initial
Exit velocity.
Yeah, the magnitude of the velocity. Okay, now we're going to take that, and we have our ballista sitting at 45 degrees. We know that this is actually a combination of vectors. That is the resultant, so 53.53 is the magnitude, so we multiply that by the sine of 45 equals VIY. 53.53 times cosine of 45 equals VIX. So that means that gives us our two vectors in those directions. Coincidentally, they're the same thing. All right, feast your peepers on this. So here's our range. We've got our ballista down here, shooting up at 45 degrees. Cool. Cool. Okay. We know that half the time it'll take to get to the very top of the parabola, half the time it'll take to get down in a perfect world. Okay. We discussed that the x velocity was 53, magnitude of velocity, so that's absolute value of the velocity, the speed basically times our cosine, because we really have two shorter legs of triangles as the vectors here. Same length as each other. Whatever. So anyway, our starting position, it's almost about 0 meters above the ground. I mean, it's almost on the ground, a couple inches up, something, whatever, a couple centimeters. So anyway, we want to find how long it takes to get up to this top point. So we find that the y velocity is the one changing the acceleration in respect to gravity. So 0 squared, vf squared equals vi squared plus 2a delta y. That's delta y, so 0 squared equals 53.53 sine 45 squared minus 19.6y. Anyway, solve for y, and you get 73.0985 meters up. So that's 73.0985 meters up direction. So we got good old question, bullet drop versus bullet fired. It's going to drop the same speed as it would if it was just not moving in the x direction at all. So anyway, we've got our function. We got xf equals xi plus vit plus 1/2 at squared. Substitute for everything, and you get 73.0985 minus 4.9t squared. Add this over, divide by 4.9. Anyway, yeah, there you go. Cool. You get the square root of that. You get t over 2. So the time it takes to get up to here is 3 point, or in respect to the time it takes to fall. Either one is symmetric about this point. We got t over 2 equals 3.86 multiplied by 2. 7.725 seconds it is in the air. So this is 7.725 seconds is our total. And we're going to multiply that by our x velocity, which in a vacuum is essentially the same all across. So we've got our VIX times our time, basically integrating for distance. Anyway, delta x, 2.9240 meters. Anyway, doesn't shoot that far, but you know, probably about half of that, roughly. But anyway, most of that could be accounted for in air resistance. Likely a good deal of friction with the band moving along the actual body of the ballista, like that. Moving there's probably a little bit of kinetic friction because rubber on wood, you know, whatever. You've also probably got a little bit of slop in our measurement of K. I mean, couldn't be too bad, but yeah.
Well, now that you've seen the math, let's head back to the garage.
Yeah.
Well, I'll see you next time on
Freak Laboratory.
Freak Laboratory.
It's busted.
Let's go.
Don't you forget about me.
All right. Good stuff.